We saw previously that one of the properties of the periodogram is that it's a biased estimator. And by this we mean that if we take the expected value of the estimate produced by the periodogram, or the periodogram estimate, it's not going to be equal to the true power spectrum of the process that we're observing, but rather it'll be the true power spectrum convolved with a squared discrete time Fourier transform of the rectangular window. And this leads to spectral leakage, because if you have an extension in frequency of this discrete Fourier transform that's induced by the window, part of the spectrum at one particular frequency will spill over into other frequencies through this convolution. In order to study spectral leakage, it's convenient to work with a sinus process, shown here with an amplitude A, frequency nu0, and random phase phi0. The reason why the sinus process is particularly suited for studying spectral leakage is that its true power spectrum only contains energy at two particular frequencies, nu0 and minus nu0. However, if we look at the bias of the periodogram, or the expected value of the periodogram estimate, we know that this is given by the convolution of the original spectrum with the squared magnitude of the discrete time Fourier transform of the window function. So we can easily evaluate what the expected value of the periodogram estimate is for the sinus process, and is given by this expression. And since the original process only contains energy at these two frequencies, we know that any energy that we observe in the periodogram estimate at any other frequency must be due to this spectral leakage. So if we want to further understand the spectral leakage of this particular process, we can look at the discrete time Fourier transform of the window function graphically, and this is what we've done here for length of n equal to 32 samples, and it's plotted in a logarithmic scale as a function of the normalized frequency. And what we can see in this window function is that it has a main lobe followed by a number of side lobes of decreasing magnitude, and it's these side lobes that are causing the spectral leakage. So if you look at a particular example for a sinus process, so in this case a sinus process with a normalized frequency of 0.1, this is what the expected value of the periodogram estimate could look like, or the ensemble average over the periodogram estimates. So it'll be the window function shifted to the position of this normalized frequency. And if you look at this, it doesn't look identical to the window function, and the reason for that is that we actually have two frequency peaks, so one here at 0.1, but there is also one at the minus 0.1, and these interact with each other, giving us something that deviates slightly from the window function. But more or less, it looks like the window function just shifted to this frequency. And if we increase the frequency of the sinus process from 0.1 to 0.2, the window function sort of shifts with the sinus process. And what we'll see is that instead of showing something which has a frequency localized at this only frequency, we'll have a broadening of the main peak due to the dimensions of the main lobe of the transfer function, and we'll have all of these side lobes also due to the window function. And this is what causes or shows up here as spectral leakage. There's a number of properties of the window and its discrete time Fourier transform that we can use in order to quantify the bias of the periodogram. So one such property is the 3 decibel bandwidth, which will denote delta nu. So the 3 decibel bandwidth is 2 times the normalized frequency at which the window has dropped 3 decibels from its main point obtained at the normalized frequency of 0. And the reason that it's 2 times this distance is that we want to measure the 3 decibel bandwidth over the complete main lobe, both for negative and positive frequencies. Another property is the so-called side lobe level, which is the ratio between the power in the main lobe and the maximum amplitude of the first or the largest of the side lobes. And this is typically specified in decibels. So for this particular example, the numbers shown are obtained for a window of length 32. So if we double this length, some of the properties will change. And what we see is that the 3 decibel bandwidth will be halved by increasing or doubling the number of samples, while the side lobe level will remain roughly the same. And this will have implications on how we choose the window length when we design our spectrum estimation meters using the periodogram. So we can look at a particular example here for a length of 32 samples. So in this particular case, we have not only one sinus process, but the sum of 2 independent sinus processes. So there'll be 2 peaks in this case for a normalized frequency of 0.1, and a normalized frequency of 0.2. And we see that the resulting periodogram, or the expected value of the periodogram, or the so-called ensemble average, is the convolution of these two peaks with the window function, and it'll turn out something like this. So in this particular case, we see that we get two main peaks resulting from the two frequencies of the process whose power spectrum we are trying to estimate. But now comes a question. What do you think will happen to the spectrum if the distance of these two frequencies is smaller than the 3 decibel bandwidth delta nu? So like shown in this particular figure. So do you think that nothing significant will happen? Do you think that the side lobe level or spectral leakage will significantly increase? Do you think that the two spectral peaks in the original process will in the estimate appear as only one peak? Or do you think it's impossible to create a signal with frequencies that are that close? The correct answer is option number 3. And we can illustrate that by looking at this example of the 32 sample-based periodogram of the sum of two sinus processes. So if the sinus processes are well separated, there is no problem in distinguishing them in the periodogram estimate that we have here. However, if the frequencies move close to each other, so within the 3 decibel bandwidth, what will happen in the convolution is that the two peaks, when we convolve them, will get smudged together and appear as only one peak. So in effect, the 3 decibel bandwidth of the window that we apply, in this case the rectangular window that we use in order to pick out the samples for the periodogram, sets a limit to the resolution of the spectrum estimate, meaning a limit to the closeness of frequencies that we can resolve in the estimate. However, we know that the width of the main peak of the 3 decibel bandwidth depends on the number of samples. So if we observe an increasing number of samples of these two sinus processes, we could end up in a situation where we again could distinguish them from each other. So in this case, we look at the case of 64 samples. And just as a reminder, all of these plots have been for the ensemble average, so averaged over all the phases in these two sinus processes, which are the only random parts of these processes. So for any particular realization of this example, it could look slightly different. However, we'll still have this discussion with the resolution remaining more or less unchanged. So the 3 decibel bandwidth is a good indicator of how close two frequencies can be in order for us to be able to resolve them properly. Another problem that could occur is if we have two sinus processes with frequencies that are in principle separable, as indicated by the 3 decibel bandwidth, but where one of the processes has an amplitude that is much lower than the other process. So in this particular example, we have such a case, and if you just look at the periodogram estimate, here in this case for a single realization, we could be led to believe that this process only contains one sinus component because that's all we could see in our estimate. And what happens here is that the second sinus process, which has a lower amplitude, is hiding within the side lobes caused by this first larger amplitude process. And this is called spectral masking. So essentially the spectral leakage from the first one spills over and hides this other frequency that we have here in the spectrum. And this problem is not necessarily fixed by increasing number of samples. So even if we increase the number of samples, in this case to 256 samples, the lower amplitude sinus process still doesn't manage to significantly extend above the side lobes caused by the first process. But we can fix this using other techniques, which we will look at next. A trick to address the problem of spectral masking is to apply another spectrum estimator, so in this case the modified periodogram. So if you recall, the periodogram consisted of taking the capital N samples from our process, computing the Fourier transform, and taking the absolute value squared, and then dividing by the number of samples. So in the modified periodogram, instead of just picking out the samples, you apply a window to them before the Fourier transform. So W of n here could be an arbitrary window chosen for its properties. And then you compute the absolute value squared of that, and you normalize, in this case with a term that involves a function of the window in order to make sure that the window itself doesn't change the absolute amplitude of our estimate. And one can easily show, like in the periodogram, that in case of the bias for the modified periodogram, it will be the true power spectral density, but in this case convolved with the squared amplitude of whatever window function we chose here. So for the periodogram, this would have had to be the discrete time Fourier transform or the rectangular window, but in the modified periodogram, we could choose an arbitrary window for its particular spectral properties. So in order to understand what we can do here, it's illustrative again to consider the discrete time Fourier transform. So in this case, for the rectangular window, which is the one that we saw, and the reason that it looks a little bit different here is that we have renormalized axis, so now it goes from minus 80 decibels up to 40 decibels. So we still have the notion of a 3 decibel bandwidth being the same as before, wavelength 32, and we have a side load level, which again is 13.2 decibels for the rectangular window. But now if we consider another type of window function, so for instance the triangular window, we'll have a different 3 decibel bandwidth. So any other window than the rectangular window will have a larger 3 decibel bandwidth. But what we get in return is a higher suppression of the side lobes, and this is what we saw in the filter design as well. So for a triangular window, the first side lobe will be a full 26.6 decibels below the main lobe. So changing from the rectangular window to a triangular window in the modified periodogram, what we give up is some resolution, but what we gain is a better side lobe suppression and less spectral leakage. And there are even better windows. So we could look at, for instance, the Hamming window, which has a very, very slight increase in the 3 decibel bandwidth over the triangular window, but has a large suppression of the side lobes, so a full 41.7 decibels in this case when we have 32 samples. And there are other windows like the Blackman window, which has even larger suppression of the side lobes at the penalty of an increased 3 decibel bandwidth. And also for the Blackman window and every other window, we could in principle increase the length of the number of samples, we increase the length of the window, so the number of samples that go into the estimate. And that would again reduce the width of the main lobe as 1 over n, or proportional to 1 over n. So doubling the number of samples will cause the main lobe or the 3 decibel bandwidth to be halved from what it was. So coming back to the example where we left off, we had the sum of two sinus processes of very different amplitudes, and we applied the periodogram to 256 samples of this process, and we couldn't see the second process due to the side lobes of this higher amplitude sinus process. However, if we change the periodogram used for this plot to the modified periodogram with a Hamming window, we have a larger suppression of the side lobe level, which now suddenly allows us to see this second sinusoid quite clearly in the side lobe levels of the main peak, or the peak corresponding to the highest amplitude sinus process. And if we change from the Hamming window to the Blackman window, we have an even higher suppression of the side lobes. So in this case, there is no difficulty in seeing the two main peaks. And the penalty we pay for that is that we have a slight broadening of both of these peaks. So we would have in principle a lower resolution, but in this case the frequencies are separated far enough for this not to be a problem. And you can compute the properties of most common windows and tabulate them. So for the rectangular window, we see that we have a side lobe suppression level of roughly 13 decibels. We have a 3 decibel bandwidth, which can be given as 0.89 divided by the number of samples. So doubling the number of samples halves the 3 decibel bandwidth and doubles our resolution. Another particular window, the Bartlett window, which is closely related to the triangular window, have a 27 decibel side lobe suppression level at a slight increase in the 3 decibel bandwidth. But the Hamming window is almost always preferable over the Bartlett window, since it has roughly the same 3 decibel bandwidth, but at a much higher side lobe suppression level. And we also saw an example of the Blackman window, which has a full 58 decibel suppression of the side lobes at an increase in the 3 decibel bandwidth. And for all windows, you'll have the same relation with n, so doubling n will halve the 3 decibel bandwidth and increase or double the resolution. We will leave the sinus processes now and return to our initial example of the AR2 spectrum. And here again we see the periodogram estimate of the power spectrum of this process, and we see that we have the problem with spectral leakage, where the true power spectral density has lower energy. So what do you think would happen in the previous example if you took the periodogram estimate and replaced it with a modified periodogram using a Blackman window? So would you have an increase in the spectral leakage and the main peaks become wider? Would you have an increase in the spectral leakage with the main peaks becoming narrower? Or would you have a decrease in the spectral leakage with the spectral peaks becoming wider? Or would you have a decrease in the spectral leakage with the spectral peaks becoming narrower? Now, the correct answer is option number 3. So the spectral leakage would decrease because the Blackman window has lower side lobe levels than the rectangular window used in the periodogram. Also, the spectral leaks would become wider because the Blackman window has a main lobe that is wider than the one for the rectangular window. And we can see that in the example. So if we take the example again with the periodogram and we replace it with this modified periodogram with the Blackman window, this is what we would obtain. So in this case, for the low frequency regions here, we would, in average, obtain a near perfect estimate. But the thing to remember here is that this is regarding the ensemble average. So if we took it for a particular instance, what we would get could look significantly different. And this is the problem of the variance of the estimate. So we haven't yet addressed that problem. We only looked at the spectral leakage, which was a property regarding the ensemble average or the expected value of the estimate. So the variance will cause several different estimates to look very different, and this is what we'll look at in the next video. But summarizing this video on spectral leakage. So what we've seen is that the periodogram has good resolution, but it suffers from the spectral leakage. So the rectangular window has large side lobes which cause this spectral leakage. So you could address this by applying instead the modified periodogram and thereby trade some of the resolution for improved spectral leakage. And the way to do this is to pre-multiply the data with a suitable window function chosen with some properties that fit your particular application or what you want to apply it for. The resolution of any window and also the modified periodogram will be increased with the number of samples. So the 3 decibel side lobe level would decrease as some constant divided by n, where this constant is dependent on the type of window that you apply. The modified periodogram solves in many cases the problem of spectral leakage. However, as we saw in the last example, it doesn't do much to improve the estimation variance, and this is what we will look at in the next video.